Thank you for the introduction. Yes, so my name is Isabel Franco Garrido, and I'm going to be speaking a bit more about quantum and also some classical optimization algorithms using Gibbs states, preparation, and beyond. So in particular, the motivation of this talk is really to search for practical quantum advantage. And one of the big candidates or strong candidates for this is quantum algorithms that prepare physically motivated states. Now, we can all imagine all the possible applications this can have for to prepare like certain physics states or quantum chemistry states like Gibbs states. It can be used for physics applications like and so on. But really, if we kind of step out, can we really harness these advances in these type of algorithms for other problems? So this is really the motivation of this talk. It's really show how certain physically motivated states, such as Gibbs states and others, are a key step in solving classical optimization problems. And so really the whole goal is to essentially try to motivate the development of more optimization-oriented quantum state preparation algorithms. So the rough outline is we're first going to cover what convex conic optimization is from scratch. Then we're going to cover what the multiplicative weights meta algorithm is. And this is the algorithm that we'll be essentially speaking about throughout the whole talk. Then we're going to go and we're going to see previous results on SDPs and LPs using this framework. And then we're going to move on to see how essentially we can extend this to other symmetric cones that were previously unexplored. And in this case, it is the second-order cone programs. And we're also going to see some quantum implementation and a classical implementation for the multiplicative weights for second-order cone programs. And then we'll just finalize with some open questions. Okay. So first, just to put all of us on the same footing, we can define convex conic classical optimization problem, and I emphasize this is a classical optimization problem, just as for instance, as a minimization of an objective function that is linear, and such that the variable you're minimizing over satisfies a set of constraints, linear constraints as we have there, and we also have some conic constraints we need to satisfy. So where the cone is just shown here as this K. And so there is nothing really much else special about this definition. Now what we can do is we can further specialize this definition, and we can just consider the case where K are just symmetric cones. And by symmetric cone, it just really just means that every point in the interior of the coin looks the same, essentially. And also it's self-dual, if that's something you're familiar with. But really, if I start naming you what the symmetric cones are, you're for sure going to have heard of them. So first, if the cone is the positive semidefinite cone, then we have the semidefinite programs. If the cone is are the positive reals, then we have linear programs, or LPs. But now maybe one that is less mentioned is the second-order cone programs, which are those where the cone is the Lorentz cone. And also there are other symmetric cones, like, but we're not really going to go into this, as these three are really the main symmetric cones used. And by second-order cone program, really the main characteristic is that this is a cone where essentially it has the property that a scalar is dominating the L2 norm of the vectors defined in the cone. And what I mean by that, I'm kind of using vague language, is that essentially we can define it as vectors where we have, I'm not going to be able, where we have like a scalar part that you can call, well, that in the literature is called, that it's this x naught, and you have a vector part. And essentially what you have is that you have vectors that have two norm upper bounded by this scalar part. And maybe it is even better seen from a picture where you just have the bigger end of your cone is this a scalar, the radius is the scalar part, is this a scalar part of your vector, and then you have your vector part are really just the vectors going on the surface of the cone. Now, you might be wondering why, maybe why should we even spend some time thinking about symmetric cones? So we have a long list of applications for each one of them. Maybe first for the SDP, you've heard about max-cut. So that's, they serve as relaxation of combinatorial optimization problems. For SDPs can also be used as in chemistry, like for electronic structure via reduced density matrices. SOCPs can, for instance, do appear in finance to do portfolio optimization, in electrical engineering to do AC optimal power flow. LPs then appear in machine learning, physics, like particle physics, and to compute discrete optimal transport. So they're really widely applicable. So it is an important, it is definitely an important subject to look into quantum advantage. So now, moving on into the actual algorithm framework, what we have is, before we start, we need to really, I need to tell you what exact formulation does the optimization problem solve. So I've defined to you, I've told you that we're going to be solving these optimization problems with, let's say, we can define its parameters like n for the cone variable size, n for the number of constraints, r for the number of cones. But really, there's a reduction that, so this problem is really just equivalent up to some polylogarithmic overhead to solving a series of problems of this form. And what is this? These are called feasibility problems. And they're just answering whether there exists an X, so there's one solution that satisfies the constraints. So you don't care anymore about the minimization. So in particular, what the multiplicative weights framework would solve is the epsilon close feasibility problems. So you're essentially solving an epsilon close optimization problem via these surrogate epsilon close feasibility problems. So just keep that in mind, because we're not going to be thinking about the minimization per se. And this is the formulation you should keep in mind. So, okay, so now we have so we know we approximately want to solve this feasibility problem here. And you should also point out that this is I've written down here meta-algorithm. So what exactly do I mean by meta-algorithm? This is just a way to say this is like an abstraction of an algorithm. So it's really just a way to, it's really just a framework that tells you roughly how the steps would go for correctness. And a lot of people know this algorithm as a mirror descent with a simple update scheme, which it's one way to see it. And here goes a very simple pseudocode for it. So in particular, just your input would be all your objective function, all your input matrices, scalars, And let's say for now, your input is also an initial solution that I will say after what exactly it is, but it is easy to implement, or it is easy to have. And the output would be this approximately feasible, or approximately feasible point, or infeasible, if the problem is infeasible. And then the way the algorithm works is that for a fixed set of t iterations, you are essentially finding a violated constraint in your solution, like just one, and updating the solution given this violation. And you continue like this until the t iterations are over, and you output whether it is feasible or not, and your feasible point. And now, if now we're going to move on to think about what is this, how the algorithm works. Well, the first thing is that, checking the step one, checking whether once one constraint is violated, you can kind of imagine it, how that can go, because, like you just check some linear constraints. But then for the second part, how exactly are you updating your solution? Like, the most important thing is you want to actually get to your answer. So how are you doing it to ensure this? And so this is where we're going to get to. But maybe a different perspective to this to this pseudocode is to check the again perspective of these meta algorithms. So in particular, let's say we have Alice and we have Bob. And the game here is that Alice wants to find a feasible point, or better said, Alice wants to find a point where Bob cannot find a violation. And Bob needs to give constantly a certificate of violation. So Alice wins if she finds this feasible, or a point that Bob cannot find, and Bob, if he can, for all the t iterations, he can always find a violation. So the way it goes is Alice starts with some guess solution 1. Bob then goes, he checks this guess solution, he finds the violated constraint, he sends the certificate. Alice, what she would then go is she would update her guess solution. And how does she do this? Essentially, the rule here is that she wants to minimize the expected losses, which would really just mean checking like having more violations in her solutions, and the solution predictability, because she doesn't want Bob to find the violated constraint. So this is roughly what she would follow. She would update and the game would go on until the final guess. And then at the final guess, either she wins and she has a feasible solution, or Bob wins because he found a violation. And then technically in the algorithm, that would mean it's an infeasible problem. But now, if we have a different look at this algorithm, and in particular, if we had a different look at what Alice is doing, she's trying to minimize expected losses, which if we map to the internal energy of the system, and if we map solution predictability to entropy, which they kind of align, then in some way she's minimizing some sort of free energy. And maybe for the physicists in the audience, this is more this is maybe a better term to think about. So in some way, Alice is trying to find the solutions that minimize this free energy. But first you should ask me, what is really the Hamiltonian we're even thinking about? We haven't even discussed about any system. So that's what we're going to get to. That's what I'm going to show you roughly what's the picture of the Hamiltonian that Alice is going to be considering. And essentially at the start, you can think that she has no information, So Alice can just start with an all zero Hamiltonian. So the whole point is that from this Hamiltonian, she needs to update given what Bob tells her, so that she ends up winning. So she ends up actually achieving the feasible point. And so the way she does it is she actually appends. So let's say Bob tells her you have the constraint, the ith constraint is violated. So what she would do is she would append this to the Hamiltonian. And maybe intuitively, like, why does this ensure correctness? Like, there is a formal way to show this, but the intuitive picture is that you are raising the energy in the directions where there are violations. And on average, this will end up giving you an epsilon approximate solution. And now, if there's also more physicists in the room, there is actually a nice, like, if we're thinking about minimizing the free energy, this is actually quite nice because we know that the solutions that she needs to use for this are actually the states of this form here, shown here. And so, okay, so sort of we have an idea of what Alice needs to be doing to update her, to update the system she's kind of considering and what solutions she has. But now, how do we map everything back into optimization? Like, we kind of maybe took some turn. So essentially, what we end up finding is that if roughly for linear programs, this is the case where the Hamiltonian is diagonal, and she needs to actually build a Boltzmann distribution, just classical distribution. However, when we're considering semi-definite programs, just by the way the problem is constructed, the Hamiltonian she has would become non-diagonal. And so this is why Gibbs preparation appear. So we get a density matrix that we need to build. Oh, yes?
Sorry, can you say again how the punishment for the entropy appears in this?
How the punishment for the entropy?
So like I see the violated constraints for raising the energy, but how do you reward high entropy in this?
How do you reward? I mean, so let's see if this answers. So essentially and I mean, maybe it's a bit, it's not kind of like I mean, I haven't seen like a formal connection with the free energy. This is more an intuitive way. But the intuition is that really what you want to compensate is you want to have like you need to minimize this quantity that is what I compare to free energy. But I mean, in some way, I think entropy would maybe be something like, because you have some, first of all, you're getting some random violation and you're essentially appending like across average with everything, like you're sort of like minimizing over that, something like that. I don't know, but there's not exactly formal. I haven't seen a formal connection with this. This is just more intuitive, so maybe it's a bit vague. But that's, yeah. I would say like the important thing is like you're minimizing entropy, something that looks like free energy. Okay, but then what we are left to kind of is that we've discussed LPs, SDPs, but we haven't really discussed the other symmetric cone that I've mentioned to you, SOCPs. And this was an open question until our work, and we'll see this in section 4. Okay, but really, so on this slide, you're going to see it a couple of times. This is really the main takeaway, I would say, from this talk. And it is that essentially, given an LP, I want you just to think that multiplicative weights requires you to build a Boltzmann distribution, a classical Boltzmann distribution. So just with some diagonal Hamiltonian. For the SDP case, I want you to have in mind that you're going to have to build so a density matrix I just have from a non-diagonal Hamiltonian. And now I'm going to show you what is the corresponding task for second-order cone programs.
Yeah. So
Yeah.
one question. Can you explain the meaning of H diagonal equals to the summation I of AI?
Yes. So this is maybe maybe the notation is I haven't really given a precise definition, but roughly for the LP case actually, these AIs will actually be strips of a matrix. So they will actually be vectors. So I mean I've kind of just given to give some kind of compact image. I've also called it AI, but technically, if you look at the LP, because X is a vector, you're just gonna, the constraints are really the strips, are really the rows of the matrix. Whereas for SDPs, because X is it's a PSD matrix, the constraint is gonna be the whole matrix A. And so they differ in that way. Q. Yeah.
Sorry, how does the T iterations, how does T depend on the parameters of the problem?
Yeah, so it's going to be, well, it's actually going to depend on which class of problems, because I think for the SDP, it depends on the cone variable size. For the LP, in the way I've described it here, I think it's going to depend on the number of constraints. And then actually for the SDP, it's going to depend on the number of cones. And then it's also going to, it's going to depend polylogarithmic on these variables. And then it's going to have also dependency on the precision parameter. Yeah. Okay, and so we're going to go into seeing what is the task we need for the second order cone.
So sorry, I don't think I listened. What's the difference between H diagonal and H non-diagonal?
So I mean, I guess here the main takeaway is maybe because I haven't precisely defined everything just for time, but really you need to be thinking that when I mean H diagonal, it just means a diagonal Hamiltonian. And when I mean H non-diagonal, it just means a non-diagonal Hamiltonian. So I would say that's the main important thing to have. So maybe don't bother too much into thinking on these AIs for each problem. Okay. And so just as a small aside, before we look into the implementation of the SDPs and LPs, maybe one of the biggest questions with classical optimization is the input model. And this is because essentially many of the classical optimization problems require an unstructured input. And essentially, for classical algorithms, this is fine because we have our classical databases. But for quantum algorithms, this is quite tricky. And I guess it's still under debate what could be implementable. But one possible solution that has appeared in the literature is the quantum state input model. And just to give a very rough feeling of what it would be, of what it is, it's essentially a way to access your input matrices in the amplitude of our quantum state. So you can essentially query the whole, for instance, row of a matrix to your database. But now, it is important to note that the implementation of this is still under debate. And there are also certain famous dequantization results following Ewing Tang's work, where under certain assumptions, essentially, you can assume you have similar classical data structures that attains comparable performance to the quantum case. So there's some ifs in this input model. But this is the one that we're going to review. So we're going to quickly review what the quantum implementation, because so far we've only really spoken about an abstract concept of an algorithm, but we haven't spoken about an actual implementation. So there is a quantum implementation of SDPs using QRAM, following some work from Appledorn, Brendau, and collaborators, where we have, again, our pseudocode. We have now a better image on how we are updating. And essentially, again, we can imagine that checking the violated constraints is fine. And the update, now we also have an image of it. And it is that we need to create a Gibbs state for it. So you have a non-diagonal Hamiltonian. And so these methods achieve unconditional square root speedups using this QRAM. And essentially doing these steps are essentially used with a mixture of QSPT, block encoding methods, and also the quantum OR lemma. But then also the quantization results apply here. And with the condition that the constraint matrices need to admit an efficient low rank representation. And that would be something like constant rank or logarithmic rank. And this is kind of like where things were at. But then recently there was also like some work by Yuan and collaborators that essentially showed that for certain constraint matrices, you can find exponential advantage. And essentially, the condition is something related to polysparsity, and they need to satisfy certain algebraic conditions. Yeah.
Do the dequantization results work by classically simulating the process of finding the violated constraints, or do they solve the original problem, like in a different way?
Do they solve? They would be for everything. Yeah. So it would. Essentially, the dequantization results, what they do is you have like an analogous classical algorithm with this like analogous QRAM classical data structure that solves the same problem in the same way. Yeah. So, okay. So then swiftly, we can also look roughly what the LPs also extends. Without getting too much into it, if you look at this paper, it's also by Appledorn and Andras Gilgen, you'll actually see that it is a zero-sum game. And that is because there's a reduction between LP feasibility and zero-sum games. And essentially, the task also goes in running multiplicative weights for both the primal and the dual problems, if maybe you're familiar with those terms. And again, the pseudocode for LP, it goes as expected, where H is diagonal. And again, it obtains similarly a quadratic speedup unconditionally. And maybe it's worth mentioning, there is also some new work where they develop a dynamic Gibbs sampler where you can they actually produce these the solutions with essentially like faster than just updating from scratch. Like they use some hints. But okay, just very briefly also, the reason why you should care about multiplicative weights is because essentially, like in the complexity, it has the leading worst case complexity with respect to the other leading algorithms. So it is a fundamental algorithm, as we can see here. But okay. Now, can we extend this? And can we find classical and quantum implementations? This is what we answer in our work. And then the main question is going to be whether also can the worst case complexity here be the leading one using multiplicative weights for SOCPs. So before our result, it was IPMs. And maybe from this big table, the only really important thing that I want you to notice is that SOCP complexity before our work was closer to SDP complexity. And the main factor here that is important is that SOCPs had this dependency on the Cohen variable dimension. So, but before this, we didn't even have a meta algorithm for SOCPs. And so you might wonder about what is the main bottleneck. And actually, the main problem is that the guess solution format for this problem is not even clear because it involves exponentiating a second-order Cohen vector. This is what we found when we actually went ahead. And what even it is to exponentiate the second-order Cohen vector, like it's definitely not element-wise because it kind of misses some properties. So what we do is we step back and we look at the algebraic context of this problem. And essentially, all the three LPs, SOCP, and SDP that I've mentioned are symmetric cones. And symmetric cones have very nice property that they are the cone on square in a Euclidean Jordan algebra. And essentially, the algebra intuitively is just one that such that if you square the element, it's positive in the right way. So for LP, positivity is coordinate-wise positivity. For SDP, it means a spectral non-negativity. And for SOCP, it means you maintain your SOCP characteristic. So this kind of this notion is what gives the corresponding algebra and the corresponding circle product to it. And essentially, we can, if you relate the second-order Cohen Jordan algebra to the SDP one, you find a way to represent second-order Cohen vectors as matrices. And these are called arrowhead matrices, which they literally look like an arrow. You have along the diagonal this scalar part. And first column, first row, you just have the vector part. And this is very nice because it has a nice spectral decomposition. Like it's all simplified here, all the non-trivial elements. So that's great. And the most important is that this relieves the bottleneck that we have, and that is that we know the solution requires an exponential of a second-order Cohen vector. And now we can simply just treat that as exponentiating the arrowhead matrix. And so we can end up with our state. And what we find is that we have a direct sum of Gibbs states where each one of the Gibbs states are built out of rank 2 Hamiltonians. I mean, they're bigger than 2 by 2, but they're all rank 2 because they're from these arrowhead matrices. And this fills in to show us how we can do multiplicative weights for SOCPs. And here we have it. So we know that the Hamiltonian is going to be a sum over certain arrowhead matrices. And now we're going to have to build this direct sum state. So we've got it completed. And so now we can go into seeing how can we implement this. So, okay, because again, I've given you now a meta algorithm that is more abstract notion of how you can do SOCPs using multiplicative weights, but I haven't really given you an exact algorithm. And so, again, we have our pseudocode that looks exactly the same as the previous ones. Now we also know the update rule. So now what we have is, okay, how can we implement this algorithm? And what we do is we extend these QRAM methods. And the main cost is then going to be, I mean, it's going to be step 1 and step 2. There's no more. And the step 1 is really going to be preparing the solutions, where preparing the solution, it just really means preparing I mean, I've given here like an approximate version of what you need to build. And that is essentially, it would be the quantum equivalent of having a direct sum. So you want to build this type of density matrices from these rank 2 Hamiltonians that you have. And you want to check the constraints. So once you've built your solutions X, you want to be checking them. And obviously as efficient as possible. So essentially, for the first task, what we've seen is that these second-order cone vectors, they have this matrix representation. And essentially, that this is a way to turn SOCPs into SDPs. So in some way, if your SOCP vector, if your second-order cone vector is in the cone, then its matrix representation is PSD. So it is that's a way to turn one from one to the other. And so then what you end up having, if you have R cones, your second-order cone solution matrix representation is going to be something very large, like Rn by Rn. It is kind of an overkill because it only really has rank 2R. So it's a shame because if we really had access to the singular value like the matrix of singular values, then we will really have something that is much smaller and it's much better to work with. And in fact, if we have access to this singular value matrix, the problem looks like it is an LP, because an LP, it's really one where it's a vector, or you can put your vector as a diagonal matrix. So this is the idea behind this is the main idea behind the algorithm on how can we turn, using QRAM, our messy Rn by Rn matrices that we're dealing with into really having a nice diagonal singular value matrix. And so, because then the complexity is going to become similar to that of LP. And so that's exactly what we do. And essentially, using QRAM, the main important building block that we use is it's the block encoding of an arrowhead matrix. And that is essentially your Hamiltonian is the sum over arrowhead matrices. So you want to block encode that so you can have easy access into building your exponential. And one rough way to think about how this goes is you have access to your input data through this QRAM. And so, and you have a very specific structure on how the arrowhead matrix looks. So you can kind of build that easily. And so once we have this block encoding of the arrowhead matrix, then you really just build your SOCP solution by having square root of R queries. And this is why square root of R. It's because to exponentiate using QSBT, you need to know the maximum eigenvalue, and essentially that's really the cost of searching for your maximum eigenvalue. But that's really just it. No dependency on n. And then there's the other part of the algorithm that it's really we want to check for the linear constraints as efficiently as possible. And I mean, just depicted here as just some linear constraint. But now, what is the main challenge in these tasks? Because I've kind of told you over the pseudocode, oh, that's fine. We can just check our linear constraints. And theoretically, it is an easy task to kind of achieve. But then because we're dealing with quantum algorithms, you actually need to measure. And that means you actually need to restart your solution, which it's something you really don't want to do, to have to pay, again, a square root of r. So the idea is that there's some, you can just really have some cheap alternatives, like running, you can do some importance sampling, and you can have like an cheap version of your solution at every round. And then you can essentially use that and avoid this cost of creating the whole thing. And that's essentially what we do. Like, we essentially get our importance weighted solutions, which we build, and then using some QSBT, so we can just transform our solutions into checking whether the constraint is violated or not, because we have access to all our inputs as we want. So the end goal is really to turn our solutions into something that looks like this, so we can just sample from it, and we're going to get with high probability the violated constraint. And so we essentially find it with some square root of r. So this would be also doing some Grover search. And okay, up to here, then this is what completes the rough overview of the quantum algorithm. But then I've also mentioned about dequantization. And I've told you that essentially you can build the same algorithm just with this alternative classical input model. So we do this as well. And what we find is that building the Gibbs states, well, this direct sum Gibbs state cost r times n queries. And checking the violated constraints cost m, which is kind of, I mean, the R and M cost is kind of expected, because I told you that both of those were search costs. So you really obtain some quadratic speedup. But then we also get some unexpected advantage on N for the quantum case with respect to this classical case, but we are not very sure whether that is something fundamental or it's a matter of looking at the algorithm more and developing more techniques for it. So we finalize our full picture of the quantum implementation, and to be honest, also classical implementation. And again, a lot of formulas here, but really the main takeaway is that now SOCP's complexities are much closer to that of linear programs. And that is relevant because linear programs are really what we can really only do in practice. Like on a day-to-day basis, people are not really running SDPs, they're really running LPs because SDPs are too costly. So bringing the algorithm's cost closer to LPs it's definitely very important. But overall, the main takeaway that you need to note is that we really have a strong feeling for saying that multiplicative weights is a very fundamental optimization technique. And so if we find good algorithms for it, it's very relevant. And so I can then go on and just maybe again show you now again the finalized slide, because this is really, if you take away anything from this talk, is this slide, the fact that each of the optimization problems requires a different state preparation. Now, obviously here, I've given you, you're not really seeing quantum states if you're thinking about quantum, but you really like, this is really like both the classical and for the quantum, like for the case of the quantum, like you really would just want to build the quantum version of these states. And And that's really what we hope we have more quantum advantage for in these optimization algorithms. And then just to tell you like a bit more on open questions and maybe on my side, some more upcoming work that I think it is relevant for this, for the multiplicative weights framework research. In particular, like I think it is important to check applications, because it is true that we might not expect to find quantum advantage for all the SDPs. I mean, perhaps it's possible, like, but it might not be the thing that we need to look for. I think we might need to focus on specific applications and really looking for advantage in certain structures. And so one of the problems that I'm interested in, that we have some coming up work, it's on the maximization of Sharpe ratio, which is it's a portfolio optimization problem. And I used to work in finance, and this is these type of NP-hard problems are actually the relevant problems where you have very bad constraints. So essentially, we take one of these bad constraints, which is the cardinality constraints, which just tells you how many assets you're allowed to put in your portfolio. And we relax it into a problem tractable by multiplicative weights. In this case, we relax it to an SDP, which, I mean, maybe still it doesn't look so nice, but it's definitely doable by multiplicative weights. And the main point that I think it's interesting here is really what we're checking is the different assumptions in the financial model and how this makes dequantization either become real or not. Because dequantization requires this hard constraint on low rank representation of your input matrices, and there is maybe no reason for certain applications to have this. But then I can also give you a few more open questions if you're interested. The main one that I guess I've repeated kind of in multiple ways is whether certain advances in algorithms such as Gibbs state preparation can they find like large quantum advantages for specific applications in optimization? Then can we also, I think what it's an interesting also approach for this algorithm is this physics, even though perhaps it's not fully formalized, is can we leverage this sort of physics feeling underneath for other implementations? Another important thing that is sometimes maybe kind of not taken care of is your final output of your algorithm is really, if you're running a quantum algorithm, it's going to be a quantum state. But let's say we're doing the portfolio optimization question. You don't necessarily want maybe a quantum state. So if you have a quantum state, what are classically interesting questions you can solve with these particular quantum states for some of the applications? And then again, using QRAM, can we defy these dequantization results? And beyond QRAM, I guess more as a field, as a question for the field is, can we find alternatives for unstructured data, essentially? I have here some of the references if anybody needs. And I'll just thank you, and I'll open for questions.